In this experiment, I tracked the oscillatory motion of a mass attached to a spring, analyzed it using tracker, and built a computational model using CloseScript to simulate the behavior. The purpose of this lab is to study the oscillatory motion of a spring mass system. Specifically, we aim to understand how gravitational potential energy, spring potential energy, and kinetic energy transfer into each other over time. This preview shows that the simulation captures the main pattern of the mass's motion, particularly the x direction, where the predicted and experimental data are closely aligned. The y position shows some deviation, likely due to limitation in modeling vertical spring oscillations. Physical principles. First, Newton's second law tells us that the net force acting on an object is equal to the rate of change of momentum. Second, we apply the energy principle. In the absence of friction or external work, the total energy in the system remains constant. The net force in this setup is the sum of gravitational force and the spring force. Gravity acts downward with the vector Fg equals 0, negative mg, and 0. The spring force follows Hooke's law, where S is the stretch or compression beyond the relaxed length. These principles help us build a motion model and energy analysis of the oscillating mass. Now for initial condition. The mass of the object is 0.42 kilograms. The calibration length used to scale the video was 0.7 meters. We use a spring constant of 6.83 newtons per meter. The relaxed length of the spring was measured to be 0.123 meters. This line sets the mass of the ball to 0.42 kilograms. This line defines the initial position of the ball based on the tracker data. Since we released the ball from rest, its initial velocity is 0 in all directions. This sets the gravitational acceleration constant near Earth's surface to 9.8 meters per second squared. It's used when calculating gravitational potential energy and force. Here we define the spring constant K as 6.83 newtons per meter. We calculated it using equilibrium conditions where gravitational force equals spring force, and it turned out to be 0.123 meters. This formula computes the kinetic energy of the system using the standard 1/2 mv squared expression. This calculates the gravitational force on the mass. It points downward and is proportional to the mass and gravitational acceleration. Here we add the gravitational and spring forces together to get the net force on the ball. This net force derives the acceleration and motion updates in our simulation. This line updates the position of the ball using its velocity and the time step delta t. It's part of the momentum principle and is essential to advance the simulation frame by frame. On the similar side, the period of oscillation matches closely. The differences appear mostly in the amplitude. This could be due to external forces like air drag or small calibration mismatches. Sources of error in both the experimental and computational model includes measurement-related errors, where the tracker tool may not always click precisely at the object's center of mass. Next, external forces such as air resistance, rotational motion, or even friction at the spring's attachment point can introduce discrepancies that won't model in the simulation. For our model, the system includes the mass, the spring, and the earth. The surroundings includes everything else, air, which could create drag. In our model system, the energy principle is satisfied. This means that the sum of changes in kinetic energy, gravitational potential energy, and spring potential energy always adds up to 0 throughout the motion. We can see from the plot that the spring potential energy and gravitational potential energy are mirror images of each other. When one increases, the other decreases, and the kinetic energy oscillates in between. Because we define the system as including the spring, the mass, and the earth, with no energy exchange with surroundings, we expect the total energy of the system to remain constant. Now let's estimate the period of oscillation from both the x and y position graphs in tracker. For the x direction, we see that it takes from 0.837 seconds to 4.843 seconds to complete 3 full cycles. That gives us a total time of 4.006 seconds, so the average period is about 1.335 seconds. For the y direction, the 3 cycles take place from 1.372 seconds to 4.843 seconds, which gives us 3.471 seconds, or an average period of about 1.157 seconds. While the periods are close, we can see that the x period is slightly longer than the y period. Still, both are within a reasonable range, and the consistency helps confirm that our spring mass system behaves similarly in both the horizontal and vertical directions.